Welcome to the fifth example in review of statics. The question reads, determine the resultant internal loadings acting on the cross-section through point B of the signpost. The post is fixed to the ground and a uniform pressure of 500 newtons per meter squared acts perpendicular to the face of the sign. Perfect stuff. Okay, so in terms of what you're given in this question, you're given that the pressure distribution or gradient or whatever you call it, basically this pressure is equal to 500 newtons per meter. So pressure is equal to 500 newtons per meter squared. And that's great, but we don't want to sum the pressures later on. We want to sum the forces or the moments, and you get moments from forces. So what do we want? We want to convert this lovely guy into a force. How do we do that? Well, we use the trusty pressure or stress equation, basically. So P is equal to F over A. How do I know the A? Well, we can easily find that. The A in this case is just where this pressure acts. So it's just 3 meters by 5 meters, right? And that's just equal to 15 meters squared. So if I isolate for force, I get that force is equal to pressure times area. What's the pressure? 500 newtons per meter squared. And then the area is 15 meters squared as we described. And you can easily, dimensional analysis is such an important tool, as you progress through the courses, because even if you didn't know this formula, you could probably figure it out just by using dimensional analysis. See, the meter squared cancels out, and you just lift with newtons, which is a force. But perfect. I will give you the lovely value. You're going to end up getting that the force is equal to 7,500 newtons. But the question of the day is, where does this lovely guy act? Well, it acts at the centroid of the shape. Since it's a square, or not a square, a rectangle, you're in big luck here. If it was a complex shape, you would have to review some different types of statics, which we're going to get into later in this course. We should review now, but it is what it is. Basically, it applies at the centroid. And the centroid of this shape is the middle. If, for example, as we know, as it says in the diagram, if I just roughly draw it, this is 3 meters, this is 2 meters, and then from here to here is 3 meters. This force will act at the center, right? So right about here. Where is that? Well, it is 2.5 by 1.5. So this is where that force is going to act. So that if the force acts right here, this right here is 2.5 meters, and then this right here is 1.5 meters. Perfect stuff. So we have the force, we know where it acts, we're done for givens. We've done more than enough, actually. Some people will delay this until the free body diagram, but it's good to establish now. Now you have everything is clear, and everything, as we said, is in givens. What does the question want us to find? It wants us to find the internal loading. What the heck is the internal loading at point B? Well, basically this says find all the possible ways, or all basically it says we want to find the magnitude of 6 degrees of freedom, basically. What 6 degrees of freedom does this lovely thing have? Well, it can move in the x direction, and we'll call this a shear force, right? Because it's shearing the beam. It can move in the y direction, and this is another shear force because, again, it's shearing the beam. It can move in the z direction, right? And this is a normal force. So those are 3. We have to check for all 3 of these. We'll do that very simply via force calculations or force summations. How about the other degrees of freedom? Well, we also have rotation. It can rotate this, the structure can rotate about the z-axis, right? So that's a moment in the z direction. It can rotate about the y-axis, a moment in the y direction, and it can rotate about the x-axis, right? So it wants us to check for all of these possible degrees of freedom, right? So we can say unknowns, and that's the internal loading. If you're dealing with a 2D problem, it's just the moment and then the x and the y, or the moment, the shear, and just m and v. That's it. The normal, the moment, and the shear. But since it's 3D, it gets more fun. Yep. So mx, my, mz, vx, vy, and then nz. Right? And then all of these are at point B. Beautiful stuff. Now we can move on to the free body diagram. And we only have one force, so this is going to be fairly simple. So FBD. And then since we only care, we're going to section the beam, and we're only going to care about this side because this is where our normal force is. So we're just going to cut the beam right here. And so basically we have the stem right here. So if we draw this guy, and this is 6 meters, and then if we draw the actual plate now, that'll kind of look like this, right? And then right around here we said is 1.5 meters. If this is 2 meters and then this is 3 meters, maybe over here we have 2.5 meters from basically this way, right? And then that means our force acts right here. So F is right here, and this is, we won't even call it F, we'll just call it 7,500 newtons. Perfect. To make stuff a bit easier, we're gonna draw, let's bring this guy down. We're gonna draw a coordinate system, just so everything is crystal clear. So if this is our Z, so this is plus Z, and then this is plus Y, and then this is plus X. Perfect. And then this is basically plus Z. Perfect. Okay, and let's even go like this. Perfect. Okay, now that's good enough for a free body diagram. What forces do we want to find? Well, we want to see if we have, let me use a third color. We want to see if we have a Vy force. We want to see if we have a Vx force, and we want to see if we have a normal Z force, right? We also want to see if we have a normal or a moment about the Y in the Y direction. We want to see if we have a moment in the X direction, and we want to see if we have a moment in the Z direction. How do we do this? Well, very simply, all you have to do is sum. You only have one force, and again, I should have did this in the beginning, but this is point B, right? And we're doing this about point B. That's very important. You're not just random, especially for the moment calculations. You're doing it about point B, but we'll get to that. Let me not confuse you. Okay. We're going to start off with the easier one. We're going to sum the forces. And by summing the forces, I hope you understand by now that we're going to get the answer to this. We're going to know, like, it's as simple, like, you may see this and be like, what the heck is going on? You're just summing the forces, you'll get these, and then you'll sum the forces and you'll get these. Simple as that. Or the sum the moments and you get those. Okay. So, number 4, sum the forces. So, if we sum the forces in the Y direction, and we set it equal to 0, we sum the forces in the Z direction, we set it equal to 0, we sum the forces in the X direction, we set it equal to 0. There are no forces in the Y direction. This is purely in the X, this 7,500 newtons, right? The only forces in the Y direction is this one that we set. Is this one that we set. And the same thing in the Z direction is the one that we set. So we're going to write them down. But in the X direction, we have Vx and we have 7,500. So be sure to include that. So the only force we have in the Y direction is the shear force in the Y direction. The only force we have in the Z direction is the normal force in the Z direction. And the only forces we have in the X direction is a positive shear force in the X direction minus 7,500 newtons, right? Abracadabra, we know one of our answers, 0 newtons. This one is 0 newtons. And this one is Vx is equal to 7,500 newtons. Beautiful. 3 of our answers right there. We need 3 more. And that simply comes from the moment summation. So we're going to sum moments. Again, in the X, Y, and Z direction. Let's start off with the X because it's the easiest. And we're going to say counterclockwise is positive. And let's just draw all of them. Y. And then some of the moments in the Z direction is equal to 0. Great, but we did forget one thing, and that is that we're taking the moments about point B, and that is very important. Okay, now we can actually look at what forces are causing a moment. Okay, so we can directly eliminate these guys because if you look at the moment equation, it's R cross F. Immediately, you understand that R is 0 for all three of these forces. Like, regardless that the force is 0 for Vy and Nz, but even for Vx, R is 0. They act at point B, so therefore the moment is 0. So the only force that can cause a moment is this 7,500 Newton force, which I'm going to call F because I do not want to say that a billion times. Okay, so this force F, what axes does it cause a moment about? Well, let's start by analyzing the y-axis, right? So this is the y-axis, and this force F is a distance, so 6 plus 1.5, that's 7.5 meters, right? And it acts right here, right? So it's 7.5 meters away from the y-axis, and it acts like so. If there were no constraints, what would this force do to the body? Well, if you can imagine in 3D, it would try and rotate this body clockwise about the y-axis, right? Clockwise about the y-axis, and that's why it causes a moment, okay? Same way in the z direction. If we draw the z force right here, or the z-axis right here, and one thing to note is that it will do a clockwise moment. So we define counterclockwise as positive, and therefore that moment will be negative. Same thing right here, away from the z-axis, it is, if you look at the diagram, trust me, it's 0.5 meters, right? And I'll even explain it. This is 2.5, right? This entire thing is 3. So therefore, this distance right here is 0.5 meters. If this is our R and this is our force, what will happen if we just let this body go? Well, this force will try and rotate it again about the z-axis in this way, if you can imagine it in 3D. And again, that is a clockwise moment, and therefore it's negative. If we define counterclockwise as positive. How about the x-axis? Well, the x-axis, it won't really do much, or it won't do anything because it's parallel to the x-axis, right? This force is like, if we were to draw a vector of this force, it would be 7,500, 0, 0. It's entirely in the x-axis, actually negative 7,500. But you get the point. It's parallel, so it will not cause a moment in the x-axis. Perfect. So I believe that is everything. We can draw everything down. So in the x-axis, we said that it will have no moment, right? So, and that's one of our answers. In the y-axis, we said that it will be equal to 7,500 newtons times 7.5 meters. And then in the z-axis, we said that it again will cause a negative moment. And then the distance is 0.5 meters. And then the magnitude of this is 3,750 Newton meters. This one is 56,250 Newton meters. And basically, those are your answers. So you've basically analyzed all 3 degrees, or all 6 degrees of freedom, and that is your answer.